So on the left is the process flow diagram of the entire plant, which was presented in the first group report, along with the main design. And on the right is the detailed design specific to the individual report in this main section, with the scrubber and all of its flows in and out, as well as the auxiliary HEPA filter unit on the gas outlet. Through extensive research on the most commonly and most economically viable scrubber units, the packed bed scrubber was chosen for the design of the main unit in this report due to its main use being for the scrubbing of NOx gases, which packed beds excel at because they have very high efficiencies of up to 99% when scrubbing a particular gas, which is needed for the NOx removal so that the plant can adhere to the Cleaner Air Act. And as well because of the fact that there should be no particulates going through the scrubber as per the main design brief, and particulates clogging up the packed bed is the main loss of efficiency in packed bed scrubbers. So the HEPA filter chosen was the H13 type, which filters out 99.95% of particulates of the worst case size. The packing choices were all investigated, and the conclusion was that for economic reasons, random packing would be chosen, and that for performance and because of their corrosion resistance due to being made of ceramic, interlock saddles would be the packing used. The design was done through all the flow rates being listed and through the use of Henry's law assumption, where the solute gas is in low concentration. That was used to find the unknown flow rates. Through these, and using the generalized pressure drop coefficient graph, the column diameter was calculated, and then through this the number of transfer units and then their heights was calculated, and then adding space for design units such as redistribution for flow and for requirements such as de-entrainers. The total height of the column was then found. Unfortunately, due to time constraints and illness, I was unable to produce an engineering drawing of the equipment. However, the main sizing is as follows. The column diameter is 0.125 meters. The column height is 13.8 meters, with 6.8 meters of 13 millimeter sized packing, 9 transfer units being used, and a transfer unit each being 0.67 meters. The auxiliary unit, the HEPA filter, had a sizing of 610 by 915 by 115 millimeters, and the wall thickness of the main unit, the scrubber unit, is 5 millimeters in stainless steel. Again, unfortunately, this section was unable to be completed before the deadline. However, multiple steps and a full second design was done in the main report in consideration of possible risks that could occur with the unit. The costings of the plant were completed and guided through similar plants and reports that had NOx removal requirements. This design was from the bottom up, chosen with economic competitiveness in mind. The capital cost of the plant is estimated to be about $850,000, and that's including all piping, connections, systems, and operation setup. The operating cost for the H2O2 and the water mainly, but also including fluid motive device costs, was estimated to be around $170,000 per annum. And in contrast with other removal systems for NOx, such as SCR, that are commonly used, that was estimated for this plant to be around $12,000 in capital cost, and a running cost of around $300,000 that would be every 4 years for change of catalyst.